Welcome to Algebra 2 Notes 1.1. Now, these notes are pretty much a review of things that you have learned in previous math classes, so we do not cover them in class. However, I congratulate you on deciding to go ahead and watch this video because they are covered, the concepts in these notes and the next couple of videos are covered on our first unit test. So this is stuff that if you do not already know, you are going to want to know. Okay, we begin by talking about real numbers and their properties. And a real number is any number that I can plot on a number line. And I'm sure some of you out there are thinking, but I thought all numbers were real. Well, we will answer your query later on in this class and say that no, not all numbers are real. And you will learn about that in just a few chapters. Now, the set of real numbers consists of two subsets. So we have rational numbers and then we have irrational numbers. And rational numbers can be expressed as a fraction, can be expressed as a fraction with a denominator other than 1, right? Because you can put anything over 1 and make it a fraction. Okay, and when they are written as a decimal, that decimal will either terminate or repeat. Okay, so can be written as fraction, and if it's a decimal, it terminates or repeats. So therefore, irrational numbers would be the opposite of that, right? So these are non-terminating, non-repeating decimals. Non-repeating. All right, so let's do some examples because it's usually easier to understand with examples. So here's my set of all real numbers. Okay, and we divide them into rational and irrational. So we said irrational are non-terminating, non-repeating. So a prime example of that would be pi, and I don't mean prime in the math sense, or square root of 2. These are numbers that just keep on going on forever when they are expressed as a decimal. And then when we move over here to our rational numbers, let's start with whole numbers. So these numbers are 0 and then all the numbers you count with, 1, 2, etc. Okay, nice whole counting numbers. Integers are these whole numbers and their opposites. So now we're talking about -1, -2, right, as well as 0, 1, 2, and so on and so forth. Okay, but now we're talking negatives as well as positives. Rational numbers are then all other numbers. So it's all of these plus everything in between them on the number line. So 1.5, 1/3, -18.75. Okay, all the other numbers that fall in between these numbers on the number line. So if we were to look to these example numbers and figure out what sets they belong to, the first question I always like to start with is, are they rational or irrational? -7. Okay, -7 terminates, so therefore it is rational. Okay, and then within the rational numbers, does it fall into one of those further subsets? Well, it's because it's negative, but it's a whole number, it's an integer. Okay, it doesn't fall into the whole number set because those can only be positive, but remember the whole number and their opposites are integers, so this is the opposite of +7. All right, 2/3, that can be expressed as a fraction, so therefore it is rational. Now, it's not a whole number, and therefore not an integer, so that's as good as it gets in terms of the subset. If you type square root of 2 into your calculator, you will see that you get a decimal, and that decimal does not terminate, nor does it repeat. So therefore, square root of 2 falls into our subset of irrational numbers. And the square root of 144, when I type that into my calculator, if I don't know what it is offhand, I'll find out that it's 12, which means because it terminates, it is rational, and it is also an integer as well as a whole number. So as I said before, if a number is a real number, then it can be written on a number line. And so we're going to ask you to do that sometimes. And I need to graph the real numbers -5/4 and square root of 3. In this class, when we ask you to graph, we want you to go ahead and put some units on your graph so we can tell that you know where we're talking about. So I'm just going to put all of the numbers between -2 and +2, and then I'm going to go ahead and plot these. -5/4, well, -4/4 is 1, so it'd be -1, and then it's a little bit more than that, so it's 1 1/4, so it'd be right around in here, and that would be -5/4. And then the square root of 3, well, I don't have a calculator, so I don't know exactly what the square root of 3 is, but I know that 1 is the same as square root of 1, and 2 is the same as the square root of 4. So I know that the square root of 3 would fall in between these two, and it's closer to square root of 4 than it is to square root of 1, so I would plot it right in here. Your point doesn't have to be exact, but it should be in the general vicinity, and it definitely should be between the two whole numbers or between the two integers that the number falls between. All right, so same thing here. We need to first order them from least to greatest and then graph them on the number line. Well, my biggest negative number, -4, is going to be my smallest number. And then let me see what comes next. We've got -1 and then -0.2. And then we start to go positive. All right, 7/10 is greater than 1/2. Square root of 2 is 1 point something. So even though I don't know exactly what square root of 2 is, I know it's bigger than 7/10. So 7/10 comes next, and then square root of 2. And again, if we're going to graph them on the number line, we need to go ahead and put some markings on our number line. So 0, -1, -2, -3. I have to go all the way to -4 because that's my lowest value. And then over here, square root of 2 is just a little bit bigger than 1. So I really only need to go up to +2 and then plot all these. So there's -4. We said -1 was right here. -0.2 is just right there. 7/10 is just a little bit greater than 1/2. So there's my 7/10. And then square root of 2 goes somewhere in here. So very important to always remember to put markings on your number line in addition to graphing the values that we've given you. So you should remember that real numbers have properties, and you should be familiar with these properties, but in case you've forgotten, let's just do a brief refresher. These properties apply to addition and multiplication, but not subtraction and division. All right, so in these examples, we are going to let A, B, and C be real numbers, because these are the properties of real numbers, and here are my properties I'm talking about. The commutative properties simply tells me that the order in which my real numbers appear changes, and yet they're still equal to each other, so that A plus B is the exact same thing as B plus A, and it works with multiplication as well. So that's the commutative. The associative tells me that the things that are associated together can change, and yet my value will stay the same. So whether I group A plus B and then add C, or I add A to B plus C group together, my real numbers are still equal to each other, and that's my associative property. And the identity property for addition tells me I add 0 to a real number and I still get that real number, or in the multiplication, I multiply that real number by 1 and I still get that real number. And my inverse tells me that in addition, I can add the opposite of a real number and I will get 0, or in multiplication, I can multiply by the reciprocal and I will get 1. Of course, this one only works if A is not equal to 0 because you cannot divide by 0. And then my distributive property simply states that whether I have two things grouped together multiplied by a third thing outside, or I've actually distributed that value, these two are equal. All right, so here's some examples. Let's identify which property the statement illustrates. So if I look at these two examples, what's going on here is that the things that are grouped together have changed. The order stays the same, right? I still have 0.6, 2.49, but the things that are grouped together, here 2.4 and 9 are grouped together, here 0.6 and 2.4 are grouped together. So when the thing that changes what's grouped together, that is my associative property. Here, 9 went from the front to the back, right? So the order changed. When I'm changing order, then I'm talking about my commutative property. Here, I have multiplied something by its reciprocal, and that is equal to 1. So that is my inverse property. Here I have added 0 to a value and I get that value. So that would be my identity property. In this one I have distributed the 5 to both the 2 and the 8. So that is my distributive property. And in this last one, there's a couple of things going on here. So first of all, I've distributed the negative. So we're going to call that the distributive property. And then I have added something to itself, or to its opposite. So I've added x to negative x, and I got 0. So that is my inverse property. And then lastly, I added that 0 to -2, and I got -2. So that is my identity property. So we've got 3 things going on here. Super fun. All right, moving down to this, which looks like a proof. And it is a proof, but it's an algebra proof, so those are the easier ones. We need to name the property used in each step. All right, so to go from this step to this step, what happened is the order of the things in parentheses changed. So when order changes, that is my commutative property. And then from this step to this step, the parentheses were around the -a plus 2, and now they're around the a plus -a, which means the things that were grouped together have changed. So that is my associative property. Here I've added something to its opposite, and it's equal to 0. That would be my inverse property. And lastly, I've added 0 plus 2, and I still get 2, so that is my identity property. Please be sure you are clear on all of these properties. Okay, last slide of these notes. So in math, we always have inverse operations. Whatever you do, you can undo. And subtraction is obviously the inverse of addition. Right? I undo addition by subtracting. And division is the inverse of multiplication. Okay, that's just a reminder, because what we're about to do has nothing to do with that. All right, let's talk unit analysis. So unit analysis is simply a way to convert one set of units to another set of units, or to simply write a problem as a pair of units. This is one you're probably pretty familiar with. You work 4 hours and earn $36. What is your rate? Well, that's your hourly wage, right? Rate is an hourly wage, and that is in dollars per hour. So we take our $36 and we put it over our 4 hours, and we find out that what I'm actually paid is $9 per hour. Right? We just use unit analysis. We wrote this as a rate. Okay, let's talk about 45 miles per hour, and we want to know our speed in feet per second. Well, this gets a little bit more complicated. So 45 miles per hour is 45 miles in 1 hour. So we need to convert the miles to feet and the hours to seconds. So let's start by converting the miles to feet. Okay, so when I want to do unit analysis, what I want to do is I want to figure out the relationship between miles and feet, and then I want to make sure that whatever that is, that my miles goes on the bottom and my feet goes on the top. So I know, because I'm smart and a math teacher, that in 1 mile there are 5,280 feet. Okay. When I go ahead and I multiply, and when we multiply 2 fractions, we multiply across the top and across the bottom. That is different from cross multiplying. So do not multiply like this, right? Straight across the top, straight across the bottom. What happens is miles divided by miles, those two cancel out, and my final answer will have feet on top. And then I need to convert my hours to seconds. Okay, well, I'm not going to go directly from hours to seconds, but I do know in 1 hour there are 60 minutes. And then because hours are on the bottom and hours are on top, those two cancel each other out. Okay, but I don't want it in feet per minute, I want it in feet per second. So now I need to convert minutes to seconds. And because minutes are on the bottom, I'm going to place minutes on the top. So I know in 1 minute there are 60 seconds. Well, now my minutes cancel each other out, and what I'm left with is seconds. So my final answer, whatever it is, and I don't have a calculator on me right now, so I'm not going to work it, it's 45 times 50 to 80 feet over 60 times 60 seconds. And that will give me my answer in feet per second. And that is the setup. And then if you actually went and did the multiplication, so you would do 45 times 50 to 80 divided by 60 times 60. And that would give you your actual rate. Right? Converting the meters per second to kilometers per hour works exactly the same way. Okay? Make sure you understand unit analysis. If you don't, Google it and watch some more videos. All right, that is all I have for today. Thanks for watching this video. And if you have any questions, be sure to ask your teacher in class. Bye.